So measuring the change in internal energy for chemical reactions. So we've learned that system and surroundings can exchange energy through heat and through work. And now we have equations for both of those. So heat would be mc delta T, and exchanging through work would be this pressure volume work. So the work is negative P delta V. So the change in internal energy during a chemical reaction is the measure of all the heat and work exchanged, right? So we said that energy is Q plus W. The change in energy is Q plus W. These could both be negative, both be positive, one or the other. Now, if we say that there's no change in volume, the W here, the W there is equal to negative P delta V. Well, if delta V is 0, what does the work equal? 0. So if there's no change in volume, then W is 0, and ta-da, the change in energy is equal to the heat exchanged. So trying to be clear, we put a little V here, and that means the heat being exchanged at constant volume. There's not any good way to look at temperature changes of individual reactants in a reaction because they're all together, right? So what we do is we measure the change of the system, the reaction, by measuring the change of the surroundings. So we can measure the change of the surroundings by very carefully controlling those surroundings, limiting what part of the universe can be affected by this heat. So one way to do this is using what's called a bomb calorimeter. So the bomb calorimeter acts as the surroundings. It's very well insulated, and so we can be pretty sure that the calorimeter is not exchanging any heat with outside. So Q for the system, that's the reaction that we're interested in, is equal to negative Q for the surroundings. If one loses heat, the other gains it. It's the same number, it's just going in different directions, so the sign is different. So we can control the surroundings by making the only surrounding that's significant the calorimeter, and so we can say Q for the system, for the reaction, is equal to negative Q for the calorimeter. So this is called calorimetry. It's literally measuring calories, measuring heat. So we measure the heat of a reaction by measuring changes in the temperature of the surroundings. So we've got the reaction either absorbing heat or giving off heat. We can't observe that directly, but we can observe the change in the surroundings. And if the volume doesn't change, no work is being done, all the energy is exchanged as heat. So here's an illustration of a bomb calorimeter. This is the bomb part. So in here is a chamber, and we've got ignition wires, and there's oxygen present in there. This is usually used for combustion reactions, and this is actually a good way to determine how many calories are in a particular kind of food. We don't do this experiment, but other schools do it, where you burn a peanut. So you stick a peanut in there and oxygen, and the ignition wires are used to start the combustion reaction, to start the burning process. So as that occurs, this is a tightly sealed bomb, tightly sealed container. The volume is not allowed to expand, and so all of the energy goes into a change in temperature as the heat. So the heat leaves and goes into the water surrounding it in this bomb calorimeter. So this is the outer part, and it's very well insulated so that we're not going to lose any heat from this water. So all the heat being given off by the reaction gets absorbed by the water, causing a temperature change in the water, and we can measure the temperature change. And we've got Q equals mc delta T, so we can look at the specific heat capacity, or the heat capacity of the calorimeter, and the change in temperature to find the amount of heat absorbed by the calorimeter and that tells us how much heat was released by the reaction. Does that make sense? So Q for the reaction, because this is happening at constant volume, is equal to the change in energy for the reaction. Here we do use a heat capacity instead of a specific heat capacity. This heat capacity is measured for a specific bomb calorimeter. Because the calorimeter itself is not changing in mass, then the C is always the same. We don't have to worry about mass or anything. Okay, so let's do a problem. When 1.550 grams of liquid hexane undergoes combustion in a bomb calorimeter, the temperature rises from 25.87 degrees Celsius to 38.13 degrees Celsius. Find delta E reaction for the reaction in kilojoules per mole of hexane. The heat capacity of the bomb calorimeter determined in a separate experiment is 5.73 kilojoules per degree Celsius. Well, there's a bunch of numbers here. Let's write them down. So we have 1.550 grams of hexane, C6H14. And we have the temperature 25.87 degrees Celsius and 38.13 degrees Celsius. Now we're doing a lot of things here with changes in temperature. These are obviously both temperatures. One must be the initial and one's the final. Which one's the initial temperature? The 25. From 25 to 38. So 25 is the initial, 35 is the final. Find delta E, heat capacity of the calorimeter, that's C, cal, that's the heat capacity for the calorimeter, 5.73 kilojoules per degree Celsius. So Q for the calorimeter is equal to negative Q for the reaction. And what we're trying to find, let me stick it up at the top, we're trying to find delta E for the reaction. This is happening at constant volume in this bomb calorimeter. So at constant volume, the change in energy for the reaction is equal to Q. So the change in energy for the reaction is equal to Q reaction, which is negative Q cal. So we need to find Q cal. Q cal equals C cal delta T. C cal here is the mass and the specific heat capacity together in one thing. Well, what's the change in temperature? It's the final minus the initial, right? 38.13 minus 25.87. $12.26 degrees Celsius. And I've got my C-cal right here. 5.73 kilojoules per degree Celsius times 12.26 degrees Celsius. What happens with the units? Degrees Celsius cancel out, right? So Q cal is 12.26 times 5.73. And checking out significant figures, this temperature difference had 4 sig figs. This has 3. That's what's going to limit things. And is so often the case, it limits it to 3 sig figs. The unit there would be kilojoules. Now, you may have or may not have noticed, when I keep the 2 extra digits, I never round that second digit up because it really doesn't end up mattering at all. And that's one of the reasons for keeping 2 digits instead of just 1. You don't have to think about rounding, just keep 2 digits and you're fine. So there's my 2 extra digits. Is this my answer? Not quite, right? We want kilojoules, but we want how many kilojoules for every mole of hexane? Is this a mole of hexane? No. How many moles is it? Could we figure that out? Sure we could. We gotta do another calculation though, right? Running out of space. Make a little space up here. We need the molar mass of that thing, right? 6 times 12.01 plus 14 times 1.008. $86.172 grams per mole for hexane. So we've got 1.550 grams of hexane. Put grams on the bottom, moles on the top, so the units work out. 86.172 down there. So we have 1.550 divided by 86.172, 0.0179872 moles. So Q-cal is this many kilojoules. That means that the calorimeter absorbed that many kilojoules. What is Q for the reaction? Negative the same number, right? So that's equal to negative Q for the reaction. I'm going to change colors because I really don't know why I'm doing this burnt orange color, although it is October, but we don't need pumpkin spice lecture notes, do we? So Q reaction is negative 70.249 kilojoules. We want kilojoules per mole. Then we divide by the number of moles that we actually had, because this is the amount of heat released for this many moles. So divide by 0.0179872 moles. $3905.5. kilojoules per mole, and that would be negative, right? 3 sig figs. If we don't want to use scientific notation, we'd call that negative 3910 kilojoules per mole. So this small amount that was less than a mole released 70 kilojoules. But if I had an entire mole, if I had more stuff, I'd get more heat out, right? So this number being larger makes sense. This is how much would be released for 1 mole. Okay, what are your questions? Yes? Then can I explain the negative and positive? I will do my best. Okay, so we've got system and surroundings. The amount of heat transferred is the same, but one is positive, one's negative. It's like a monetary transaction. I give you $10. For me, that's negative 10. For you, that's positive 10. But from your perspective, well, never mind. I don't know where that was going. Anyway, so here we have the two people exchanging money. It's negative for one and positive for the other. Depends on who you're looking at, right? You okay with that? So I calculated the amount of heat absorbed or released by the calorimeter, because that's what we can measure, the temperature change in the calorimeter. So that's the heat capacity times the change in temperature. So that gave me a positive number. That means that the other part is also 70, but the sign is opposite. So if Chris gives me $50, and we can look in my wallet and say, oh yeah, you've got plus 50. How do we find out how much money he lost? Well, it's the opposite, right? It would be negative 50 for him, positive 50 for me. Or maybe let's think about checking and savings account. I transfer $50 from my checking account to my savings account. So in my savings account, it says plus 50, and in my checking account, it says negative 50. So whether the number is positive or negative just depends on which account you're looking at. Does that make sense? Kind of?
So in terms of energy, the energy is being transferred from
For this reaction, it's being transferred from the chemical reaction to the calorimeter. The calorimeter is the surroundings. We don't have to worry about what's outside the calorimeter because the calorimeter is well insulated and it's not going to lose any of that heat. So this is our system, this is the surroundings. We can measure the temperature change in the surroundings, but not in the reaction. So we measure this one, and we know that the other is the same value, but the sign is different.
So energy is going from the reaction to the product?
Yes, the energy is going from the reaction to the calorimeter. So we've got combustion, right? Something's burning, it gets hot, right? So you burn something in this little container surrounded by water, where is that heat going to go? It's going to go into the water and warm up the water, right? And we can measure the temperature change of the water. Any other questions?